class. Welcome to EdVantage. I'm Dr. Scott Adamson, and today we're going to explore a classical calculus problem. This problem context has been in calculus textbooks probably since Isaac Newton. Okay, maybe not quite that long, but for a long, long time. You probably have, if you haven't already seen this problem in your book, you will. The problem is this. A 10-foot ladder is leaning against the side of a house. As the foot of the ladder is pulled away from the house, the top of the ladder slides down along the side. The foot of the ladder is pulled away at a rate of 2 feet per second. How fast is the ladder sliding down when the foot of the ladder is 8 feet from the house? So what we're going to do first is explore the situation on Desmos, then we'll come back and actually solve the problem.
So before we solve this problem, you can take a look at it again here in writing. We're going to actually simulate this sliding ladder problem. So notice here in Desmos, I can grab the foot of the ladder, as the problem states, and I can pull it away from the house. And as I do, notice the top of the ladder sliding down the side of the house. And the question that we're going to explore is, when I pull the ladder away from the house, at the moment that it is 8 feet away, right there, how fast is the top of the ladder actually sliding down the house? Now, a couple of things to notice is, first of all, if I click play, notice that as the foot of the ladder is sliding away from the house at a constant speed, the top of the ladder does not fall at a constant speed. Notice here at the beginning it's a little more slow, and as we get towards the bottom, the ladder is falling. That vertical height is changing very quickly. So the question is, at this moment, when the foot of the ladder is 8 feet from the wall, how fast is the top of the ladder sliding down the wall? And we will be able to use our knowledge of derivatives and rate of change to actually solve and answer this question.
So as you've seen with Desmos, that ladder is sliding away from the wall, and as it does, the top of the ladder falls. And what we've seen is, even though we're sliding the foot of the ladder away at a constant rate of 2 feet per second, the top of the ladder is falling more slowly in the beginning, and then faster, 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 faster as it falls. And what we want to explore is, how fast is the top of the ladder falling at the moment we reach this place where the foot of the ladder is 8 feet from the wall? So before we actually engage in solving the problem, I just want you to be aware of these different changing quantities. The first one I want you to think about is that quantity I'm calling W. W is the distance the foot of the ladder is from the wall. And as that foot of the ladder gets pulled away from the wall, over time, that distance is increasing. Now maybe if we walked up to this situation, the ladder would be leaning up against the wall, and it would be maybe a certain distance away from the wall, maybe a couple of feet. Then we grab the ladder and start pulling it away at a constant rate of 2 feet per second. That distance versus time graph would look something like this. At time 0, the distance would be something. Let's just say it's 2 feet from the wall at that moment. And if we're pulling it away at a constant rate of 2 feet per second, that is, if 1 second elapses, we pull it away 2 feet. Another second elapses, another 2 feet, etc., etc., etc. What we would create is a linear function about like so. What's important to realize here is that this distance W, that horizontal distance from the wall, is changing linearly in this case as a function of time. And we could even identify what this function is. That function W would be, with a vertical intercept of 2, starts at a distance of 2 feet from the wall, and then increases in distance at a rate of 2 feet per second for however many seconds elapses. Now what's cool about this whole related rates of change thing is, you don't have to even know what that function is. In fact, in other cases, we're not going to know the exact function formula like we do here, but I just wanted you to be aware that this function exists, and sometimes we'll know exactly what that formula is, and other times we won't. For example, let's look at this next one. I'm calling the how high above the ground the ladder is, I'm calling that distance h. And h starts out relatively high, and as the foot of the ladder moves away from the wall, that distance h gets smaller and smaller and smaller and smaller. And as you saw in Desmos, initially, so when time is 0, that height is relatively large. And initially, if time goes on, the height didn't change dramatically. It was moving, the ladder was moving relatively slowly at first. But as time went on, that ladder fell, that vertical height was changing more quickly, more quickly, more quickly, more quickly, more quickly. And in fact, towards the end, we saw it falling pretty fast in that simulation. And so at the end, if you increase time by a little bit, that height is going to drop much more significantly. And so the graph that we would see here is not linear at all. Now, I don't know exactly what function formula would be used to model this situation, but it is important to realize that that height is some function of time. And the cool thing is, we don't have to know exactly what that function formula is. We just have to know that the function exists, and we could sketch it out graphically. There's one more quantity I want you to pay attention to here, and that is the length of the ladder itself. As you pull the ladder away from the wall, the foot of the ladder away from the wall at that constant rate of 2 feet per second, and the height of the ladder, the top of the ladder, gets closer and closer and closer to the ground, the length of the ladder will never change. The length of the ladder, which could be another function of time, is always 10 feet. So when time is 0, the length of the ladder is 10 feet. As time goes on, the length of the ladder just stays 10 feet. So we have a third function here. We would call this a constant function, and we could write the formula. It's just the length of the ladder is the constant 10. It's always 10 feet long. But again, it's not important that we know the exact formula for this function. We just have to know that the function exists. Now, one more thing before we solve this problem is that variable w, that horizontal width, we could call it, from the base of the wall, that height that the top of the ladder is from the ground, and that length of the ladder, those three quantities can be related by the ever-famous Pythagorean Theorem. That w squared plus h squared is equal to L squared. So the leg squared plus the other leg squared is equal to the hypotenuse squared. And in our case, what we are really interested in is when that w, when that width from the wall, or that distance from the wall is 8 feet. At that moment in time, how high above the ground is the top of the ladder? The length of the ladder, again, is always 10 feet. So we can actually find that height, that distance from the ground at that moment that the width or the horizontal distance is 8 feet. 8 squared is 64. 10 squared is 100. That means that h squared has to be 36, since 64 plus 36 is equal to 100. And then what variable, what quantity squared would give you 36? Well, 6. So we know that at the moment in time that we're interested in, the height of the ladder is 6 feet above the ground. Let me mark it here. When the distance from the wall is 8 feet. And knowing all of that, we can now determine how fast is the ladder actually falling at that specific moment in time. So we've established that at a moment in time that all of these quantities are changing. Remember, the ladder is actually being pulled away from the wall. The top of the ladder is falling down. So things are moving. But at an instant in time that horizontal distance is 8 feet, that vertical height is 6 feet. But things are still moving, and we want to know how fast is that vertical height changing at that moment. So let's return to our Pythagorean theorem. W squared plus that h squared is equal to L squared. But remember earlier we were looking at those three functions, that w quantity is actually changing with respect to time. H is changing with respect to time. L is the length of the ladder. It's not actually changing with respect to time. It's a constant function 10. But these three quantities are all functions. So in our mind, and I'm going to write it, but in your mind, we want to think this w quantity was actually a function of time. And this h quantity was another function of time. And this L quantity was also a function of time. And the reason we want to keep that in our mind is these aren't just single variable quantities, W, H, and L. These are changing quantities, changing relative to time. So this is a function of time. We actually could determine what that function is. It's 2 plus 2t. Or this is a function of time, that vertical height. We don't necessarily know what the function formula is, and we don't need to, but we know that the function exists. And then this is a function of time, constant function. L is always 10 in this case, but it is a function of time. What we want to get to now is, how can we express how all these quantities are changing? The derivative, the rate of change. So we're going to take the derivative of all these quantities using the chain rule. So first, power rule. The 2 comes down front. We decrease that power by 1, so it'll be to the first power. And then by the chain rule, we have to take the derivative of that function. Now, I know what the function is, and I could take the derivative of it, and so could you. But we're not going to actually take the derivative. We're just going to express it symbolically. We're going to say the derivative f prime of t. Likewise here. Power rule, 2 drops down front. Decrease the power to 1, and chain rule, take the derivative of g of t, g prime of t. Over here, 2 drops down front, decrease the power to 1, chain rule, take the derivative of our function, h of t, and just call it h prime of t. Now, that's the kind of the gory details of it all that I want you to have in your mind, but you may not always write it all out. Oftentimes, if you look in a textbook or online, you might see it written this way. The 2 gets multiplied by f of t, which we were calling that distance w in our diagram. The derivative we could express using the Leibniz notation as dw dt. So rather than the function notation, we'll just go back to the actual variables that we had in our diagram and say 2w dw dt, and 2h and dh dt. And then over here we have 2 times, that was L, and then the derivative in Leibniz notation would be dl dt. Now remember, the goal of this problem is to determine how fast is that vertical height changing at the moment in time that the ladder is 6 feet from the wall. That is, we want to know this. So we just can do some algebra now and determine what that quantity would be. So the first move of algebra would be, let's take this term and subtract it to the other side. So 2h dh dt will equal 2l dl dt minus, we're going to move that term over, so 2w dw dt. Again, remember we're solving for dh dt. How fast is that height changing at a moment? So we'll just divide both sides by 2h. So here it is. dh dt is going to be found by taking 2 times L times dl dt, subtracting 2 times w times dw dt, and dividing all of that by 2h. Now that's just the general formula that we could use to determine how fast is that h quantity, that vertical distance, changing at any moment that we like. But in the problem I asked you to solve, the moment was when the distance from the wall was exactly 8 feet. So let's now just determine all of these quantities at that moment in time. So 2 times L. Remember, L is the length of the ladder, 10 feet. dl dt, the rate at which the length of the ladder is changing. The length of the ladder is not changing. So dl dt is 0. Now this is very nice because 2 times 10 times 0 is just going to give us 0. Minus 2 times w. Now in the problem statement, w was the 8 feet. When the ladder is 8 feet from the wall, dw dt. How fast is w changing? The problem told us that the ladder is being pulled away from the wall at a rate of 2 feet per second. Divide all that by 2 times h, 2 times h. We saw earlier that when the ladder is 8 feet from the wall, the height would be 6 feet. So, some quick arithmetic here. 2 times 10 times 0, 0. 2 times 8 times 2. It's going to be 32, but notice we're subtracting, so it's going to be a negative 32. Divided by 2 times 6 is 12. So negative 32 twelfths, simplified, let's see, that'll simplify to negative 8 thirds feet per second. So at the moment in time that ladder is 6 feet from the wall, 8 feet from the wall, and the ladder is 6 feet above the ground, that height is changing at negative 8 thirds feet per second. Now why negative? That h distance is getting smaller and smaller and smaller as the ladder falls. And so the rate of change is negative to indicate that. And the rate is specifically 8 thirds feet per second. So yes, we've solved the problem. Negative 8 thirds feet per second is how fast the top of the ladder is changing. But maybe we want to figure out the speeds at different points in time or different moments, that the different distances that the base of the ladder is from the wall. And so we might want to come back to this result and just clean it up a little bit, simplify it, make things a little easier to work with. In this particular problem, the length of the ladder was 10 feet, and that length never changes. The length of the ladder does not ever change. So the rate at which the length is changing relative to time is 0. Keep in mind, back on our function, it was a constant function, that horizontal line. And so the derivative, the slope of that function, would be 0. In our case, the width of the ladder is changing. Now, we stopped it when W was 8 previously, but what if you wanted to examine different lengths from the wall? Well, we could just leave that W and ultimately substitute in a little bit later. And in our case, dw dt was the 2 feet per second, the constant rate that we were pulling the ladder from the wall. All of that gets divided by 2h. And remember, h was the height above the ground. The top of the ladder is at a moment in time. So let's just clean this up and make it look a little prettier. 2 times 10 times 0 is 0, minus, this could be expressed as 4w divided by 2h. And then we can simplify that even more. 4 divided by 2 is 2, so we could just say negative 2w divided by h. So, if you want to know how fast is the height of the ladder changing at any moment, any distance at the bottom of the ladder is from the wall, you just need to know those two things. And if you know those two things, you can determine that rate. And that rate would be measured in feet per second. Now notice just one thing about this result. At some point in time, the height of the ladder above the ground is going to be 0. And at that moment in time, we have what we call a model breakdown. Because when h is 0, this rate of change doesn't exist. And in fact, the smaller h is, the closer to the ground that ladder gets, the faster, in a negative direction, the faster that rate of change is. So for values near the ground, we're going to get extraordinarily large rates of change. So the model kind of fails us for lower heights. But for heights greater than that, arbitrarily heights that aren't going to be so close to 0 that this explodes, it gives us a pretty good idea of how fast the top of the ladder is changing relative to time.